You're resting peacefully, perhaps feeling the soft weight of a cozy blanket or the gentle, rhythmic motion of your own breathing. As the world outside begins to hush its busy sounds, a familiar sense of peace might settle gently over you, the quiet wonder of looking up at the night sky. Imagine countless stars, scattered like shimmering dust across an endless canvas of velvet black, each one a distant, luminous whisper of creation. They seem to occupy a vast, silent expanse, stretching out in every direction, an endless cosmic ocean. This profound sense of boundlessness, of infinite space, feels so perfectly natural, so wonderfully serene. But tonight, we'll softly ponder a profound cosmic enigma, a whisper from the very fabric of existence that suggests this vast universe is changing, expanding, and perhaps doing so with a quiet acceleration that surprises even our deepest understanding. We often perceive space as simply there, an empty stage where the cosmic drama unfolds. We think of it as a passive container, vast and unchanging, holding all the stars, galaxies, and nebulae in their appointed places. But if you allow your thoughts to linger, to softly trace the edges of this everyday certainty, you'll discover that space itself is far more dynamic, far more wondrous than a simple static void. It is an active participant in the cosmic ballet, a fluid, responsive medium that can gently stretch and expand, carrying everything within it along for a profound, unhurried journey. This understanding transforms our view of the universe from a mere backdrop to a living, breathing entity, perpetually in motion. Imagine, if you will, the universe in its earliest moments, a profound, almost unimaginable state of cosmic infancy. The popular scientific narrative of the universe's beginning is often described as the Big Bang. But let's gently soften this image, stripping away any sense of sudden, jarring chaos. Instead, imagine it as an infinitesimal point of immense energy and profound order, a cosmic seed containing all the potential for the universe that was to come. In this earliest, most serene state, the universe was incredibly compact, with all its energy and matter gently condensed into an unimaginably small, uniform region. And from this tiny, perfect cosmic seed, space itself began its grand, subtle journey of expansion. This initial expansion was not an outward explosion of matter into existing space, but rather a gentle stretching and growth of space itself, carrying matter along with it, like currents slowly moving apart in a gently rising loaf of baking bread. As the dough expands, the currents move further from each other, not because they are actively moving through the dough, but because the dough itself is growing. In the same way, galaxies are not hurtling through space away from a central point. The space between them is simply getting larger, subtly increasing its own volume, carrying the galaxies along for the ride. In the very early moments after this quiet beginning, this cosmic blossoming, the expansion was incredibly rapid, a swift, almost silent inflation of the cosmos. Think of it as a vast, invisible balloon being inflated with astonishing speed, its surface stretching smoothly outwards. As the universe continued to expand, it also cooled, gently allowing the fundamental particles that filled its early moments to coalesce. Over immense spans of cosmic time, millions, then billions of years, these basic building blocks, guided by the subtle forces of gravity, patiently formed the first atoms, and then, eventually, the magnificent galaxies we gaze upon today. This process of expansion, of space subtly increasing its own volume, has continued for billions of years, creating the vast, boundless cosmos we inhabit. The understanding of this cosmic expansion is a relatively recent, profound revelation. For centuries, thinkers imagined a static, unchanging universe. It was only in the early 20th century that patient observations of distant galaxies began to reveal a surprising truth. Almost all galaxies are gently moving away from us, and the further away they are, the faster they appear to recede. This consistent outward movement is not because galaxies are hurtling through space away from a central point. No, it's because the space between the galaxies is expanding, subtly increasing its own volume, carrying the galaxies along for the ride. Imagine the universe as a vast, gentle balloon, and the galaxies as dots painted on its surface. As the balloon is softly inflated, the dots move further apart, not because they are moving across the balloon's surface, but because the surface itself is growing. This majestic expansion felt, for a long time, so perfectly ordered, so wonderfully understood. The laws governing it, like the intricate balance of gravity and the initial conditions of the Big Bang, provide clear guidelines for how fast the universe should be expanding and how that expansion might change over cosmic time. For a long time, it was widely believed that the gravitational pull of all the matter and energy within the universe would subtly slow this expansion down, perhaps even causing it to eventually halt, or even gently reverse into a big crunch. Gravity, that pervasive, gentle persuader, was seen as the cosmic anchor, always seeking to pull things back together, to slow the outward journey. But what if, in the vast, unexplored reaches of the cosmos, something were quietly happening that defied this well-understood expectation? What if the expansion of space was not slowing down, but was, in fact, subtly speeding up, accelerating with a quiet, persistent force that surprises even our deepest understanding? This is the profound enigma that has emerged from the patient observations of modern cosmology, a universe that is expanding faster than it should, challenging the very fabric of our celestial understanding and hinting at a deeper, more mysterious layer of cosmic truth yet to be unveiled. This isn't about dramatic, sudden bursts of energy or violent cosmic cataclysms. No, this is about the subtle, continuous unfolding of the universe, serenely expanding, yet whose very behavior suggests a hidden, pervasive force subtly pushing it outwards, a force that gently lies beyond our current grasp. It invites a quiet questioning, a humble re-evaluation of the elegance of our physical laws. It prompts scientists to softly explore the edges of their current models, to seek out new, delicate nuances in the grand cosmic tapestry. The very existence of this unexpected acceleration becomes a luminous guide, drawing our curiosity towards unseen pathways in the vastness of space. Consider the immense patience of observation required to identify such an anomaly. Astronomers, like diligent cosmic gardeners, spend countless quiet hours gazing at the night sky, meticulously charting the positions and movements of distant galaxies. It is only through this patient accumulation of data, this gentle vigilance, that a subtle deviation, a whisper of an impossible acceleration, might finally emerge from the luminous background. And once identified, the quiet work of analyzing its light, its distance, and its apparent speed begins, each piece of information gently confirming its enigmatic status. This initial encounter with a universe that seems to expand with an unexpected vigor invites a profound sense of wonder, a gentle questioning of what else might be hidden in the vast, unexplored archives of the cosmos. It suggests that our understanding of cosmic evolution might be more like a winding river with unseen tributaries and forgotten bends, rather than a straight, predictable path. And in this gentle uncertainty, there is a deep comfort, a reassurance that the universe's capacity for profound understanding and astonishing phenomena has always been a quiet, persistent force, blossoming in unexpected moments throughout the tapestry of time. So, as you continue to relax, allow your mind to gently contemplate the feeling of gazing up at the night sky, sensing the quiet wisdom it might contain, and then imagine space itself, silently expanding, gently carrying the stars and galaxies further and further apart. Feel the profound peace that comes from understanding that the universe is not a closed book, but a vast, ongoing story, with new, wondrous chapters always waiting to be gently turned. Let this understanding cradle your consciousness, like the serene, unwavering passage of cosmic light itself, as you gently surrender to the peaceful, restorative depths of slumber. The quiet whisper of a universe expanding faster than it should, waiting patiently to be understood, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, always guiding us towards the serene future. You're floating deeper now, gently carried by the quiet understanding of cosmic space, subtly expanding and embracing all within it. As you drift, let's cast our gaze much, much further, back to the very dawn of our universe, to a time of profound simplicity and exquisite order. Imagine not a noisy, chaotic explosion, but a serene, almost unimaginable state of cosmic infancy, where energy was perfectly balanced, perfectly contained. This is the serene essence of the universe's quiet dawn, how its earliest moments held a profound cosmic order, a silent, singular arrangement that set the stage for space's grand, unhurried expansion. The popular scientific narrative of our universe's beginning is often referred to as the Big Bang. But let's gently soften this image, stripping away any sense of sudden, jarring chaos. Instead, imagine it as an infinitesimal point of immense energy and profound order, a cosmic seed containing all the potential for the vast, intricate universe that was to come. In this earliest, most serene state, the universe was incredibly compact and astonishingly uniform. All its energy and matter were gently condensed, evenly distributed throughout every minuscule region, like a perfectly blended smooth, warm liquid, with almost no discernible ripples or variations in its cosmic texture. It was a state of immense, profound simplicity and exquisite, singular order. From this tiny, perfect cosmic seed, space itself began its grand, subtle journey of expansion. This wasn't an outward explosion of matter into existing space. No, it was a gentle stretching and growth of space itself, carrying matter along with it, much like currents slowly moving apart in a gently rising loaf of baking bread. As the dough expands, the currents move further from each other, not because they are actively moving through the dough, but because the dough itself is growing. In the same way, galaxies are not hurtling through space away from a central point. The space between them is simply getting larger, subtly increasing its own volume, carrying the galaxies along for the ride. In the very early moments after this quiet beginning, this cosmic blossoming, the expansion was incredibly rapid, a swift, almost silent inflation of the cosmos. Think of it as a vast, invisible balloon being inflated with astonishing speed, its surface stretching smoothly outwards. As the universe continued to expand, it also cooled, gently allowing the fundamental particles that filled its early moments to coalesce. Over immense spans of cosmic time, millions, then billions of years, these basic building blocks, guided by the subtle forces of gravity, patiently formed the first atoms, then the first stars, and eventually, the magnificent galaxies we gaze upon today. This process of expansion, of space subtly increasing its own volume, has continued for billions of years, creating the vast, boundless cosmos we inhabit. The understanding of this cosmic expansion is a relatively recent, profound revelation. For centuries, thinkers imagined a static, unchanging universe, a fixed stage for the celestial drama. It was only in the early 20th century that patient observations of distant galaxies began to reveal a surprising truth. Almost all galaxies are gently moving away from us, and the further away they are, the faster they appear to recede. This phenomenon, known as Hubble's law and the cosmological redshift, provided the first direct observational evidence that the universe is indeed expanding. The light from distant galaxies appears red-shifted because the space it's traveling through is gently stretching, effectively lengthening its wavelengths, making it appear redder, much like the pitch of a siren lowers as it moves away from you. This majestic expansion felt, for a long time, so perfectly ordered, so wonderfully understood. The laws governing it, like the intricate balance of gravity and the initial conditions of the Big Bang, provided clear guidelines for how fast the universe should be expanding and how that expansion might change over cosmic time. Based on the amount of matter and energy observed in the universe, it was widely believed that the collective gravitational pull of all this cosmic material would subtly slow this expansion down over vast stretches of time. Imagine throwing a ball into the air. Gravity will eventually slow it down, perhaps even cause it to fall back to Earth. Similarly, gravity, that pervasive, gentle persuader, was seen as the cosmic anchor, always seeking to pull things back together, to slow the outward journey, perhaps even causing the universe to eventually halt its expansion, or even gently reverse into a big crunch. This concept of a decelerating expansion felt intuitively correct, a harmonious balance between the initial outward push of the Big Bang and the relentless inward pull of gravity. It provided a comforting sense of predictability to the universe's grand unfolding, a narrative where cosmic forces were in a profound, understandable tug-of-war. The vast cosmic stretches of time ahead seemed to be governed by a gradual slowing, a gentle, inevitable yielding to the collective gravitational embrace of all the matter within. It was a beautiful, elegant picture of cosmic destiny, patiently revealed through the soft whispers of mathematics and astronomical observation, a general historical fact that highlights this revolution in understanding the universe's beginning before the 20th century. The concept of a beginning to the universe was often a philosophical or religious idea. The scientific evidence for the Big Bang, patiently gathered over decades, including the discovery of the cosmic microwave background radiation, the faint uniform glow of residual heat from the early universe in the mid-20th century, provided compelling evidence for a universe that began in an incredibly hot, dense, and remarkably uniform state, perfectly aligning with the concept of an initial low-entropy condition. This quiet hum from the cosmos became the most powerful evidence for a universe that started small and has been growing ever since. Here's a lesser-known detail about the early universe's remarkable uniformity. The cosmic microwave background radiation is incredibly uniform across the entire sky, varying by only about 1 part in 100,000ths. This subtle, almost perfect uniformity is a profound testament to the exquisite order of the universe in its earliest moments. These tiny, almost imperceptible variations, however, are also crucial. They are the gentle seeds from which all the large-scale structures we see today, galaxies, galaxy clusters. And the vast cosmic web eventually grew through the subtle, persistent pull of gravity over billions of years. It's like a perfectly blended, smooth canvas, with only the faintest, almost imperceptible brushstrokes hinting at the grand masterpiece to come. And for an ongoing academic debate, physicists are still actively researching the precise nature of the universe's initial low-entropy state. Why did the Big Bang start with such a remarkably low entropy? Was it a natural consequence of the cosmic expansion itself? Or does it require a deeper explanation related to quantum gravity? Or the nature of spacetime before the expansion began? This fundamental question about the initial conditions of our universe remains one of the deepest and most beautiful puzzles in modern cosmology, revealing the subtle wisdom of reality's grandest rhythms and the profound challenges at the very edges of our understanding, inviting continuous, gentle inquiry into the ultimate origins of everything. So, as you continue to drift, allow your mind to gently contemplate the universe's quiet dawn, that serene, singular arrangement of cosmic matter and energy. Feel the profound peace that comes from understanding how its earliest moments of exquisite order set the stage for space's grand, unhurried expansion, gently guiding everything outwards. Let this understanding cradle your consciousness, like the serene, unwavering passage of cosmic time itself, as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of cosmic expansion, a testament to the universe's profound ability to create boundless space from a tiny seed, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most fundamental aspects of our cosmic tapestry, forever guiding us towards the serene future. You're floating deeper now, gently carried by the quiet understanding of the universe's serene, unhurried expansion. As you drift, let's turn our attention to a pervasive, unseen sculptor that has long been thought to gently slow this grand cosmic unfolding gravity. Imagine it not as a forceful tug, but as a subtle, pervasive embrace. A gentle anchor pulling everything inward, constantly seeking to bring the vastness back together. This is the serene essence of when matter softly pulls back, a profound cosmic tug-of-war where the collective embrace of all that exists quietly works to decelerate the universe's outward journey. For billions of years after its quiet dawn, the universe expanded. But this expansion was generally thought to be gradually decelerating. The reason for this expected slowdown lies in the very nature of matter and energy that fill the cosmos, and their inherent gravitational attraction. Every star, every planet, every galaxy, every particle of cosmic dust, however small, exerts a gravitational pull on every other particle. It's like countless tiny, unseen threads, perpetually stretching across the vast expanse, each one gently tugging, drawing everything towards everything else. Think of it like throwing a delicate pebble softly upwards into the vast, open air. As the pebble rises, the Earth's gentle gravity continuously works to slow its ascent, eventually causing it to pause and then gracefully fall back down. Similarly, the initial outward push of the Big Bang, that immense primordial energy, sent the universe expanding outwards. But the collective gravity of all the matter and energy within the universe was thought to act like a cosmic anchor, a pervasive, gentle persuader, constantly working to slow down that outward journey. The more matter and energy there was, the stronger the collective pull, and the more rapidly the expansion was expected to decelerate. Traditional cosmological models, for much of the 20th century, beautifully predicted this deceleration. They suggested that the ultimate fate of the universe depended on a delicate balance if there was enough matter and energy, gravity would eventually overcome the expansion, causing the universe to gently halt its outward growth and perhaps begin to slowly contract, eventually leading to a big crunch, a graceful regathering of all cosmic material back into a dense, primordial state. If there was too little matter, gravity wouldn't be strong enough to stop the expansion, and the universe would continue to expand indefinitely, but at an ever-slowing pace, gradually fading into a cold, dark stillness. This was a harmonious dance between the initial push and the gentle, persistent pull of gravity, a predictable rhythm to cosmic destiny. In these traditional models, the universe was always conceived as being in a state of a cosmic tug-of-war, with the initial energy of the Big Bang pulling outwards and the gravitational embrace of matter pulling inwards, the visible galaxies, the dark matter, that mysterious, unseen form of matter that also exerts gravity, and all other forms of energy that respond to gravity were considered the primary forces shaping the universe's ultimate expansion or contraction. The expectation was always that gravity would win, or at least continuously slow down. The outward rush, like a gentle current slowly losing momentum as it spreads across a vast lake. Consider the immense scale of this cosmic deceleration. Even if the universe was slowing down, this process would unfold over billions, even trillions of years. The slowing would be imperceptible in any human timescale, a profound, unhurried act of cosmic deceleration. Stars would continue to shine. Galaxies would continue their gentle rotations, all while the vast space between them subtly, imperceptibly, expanded at an ever-decreasing rate. It was a picture of a universe moving towards a serene, predictable equilibrium, patiently guided by the gentle hand of gravity. A general historical fact that highlights this long-held belief. For decades after Edwin Hubble's groundbreaking observations of the expanding universe in the late 1920s, the primary focus of cosmology was on measuring the rate of this expansion and determining whether gravity would eventually cause it to slow down enough to lead to a big crunch or a perpetually, but slowly, expanding universe. The idea of a decelerating universe was a cornerstone of cosmological thought, a logical consequence of gravity's gentle pull on all cosmic matter. Here's a lesser-known detail about the subtle influence of gravity in the early universe. In the very early moments after the Big Bang, when the universe was incredibly dense, gravity's pull was much stronger, acting as a very effective brake on the expansion. This intense gravitational braking helped to smooth out initial irregularities and allowed matter to gently clump together, eventually forming the seeds of galaxies and larger cosmic structures. So, gravity wasn't just slowing expansion, it was also subtly shaping the very large-scale architecture of the universe, orchestrating the early cosmic dance. It's like a quiet, unseen hand, gently molding the clay of the early cosmos, and for an ongoing academic debate. While the concept of a decelerating universe dominated for a long time, the precise amount of dark matter and its gravitational influence is still a major area of research. How much of this mysterious, unseen matter truly exists? And how exactly does its gravitational pull contribute to the overall cosmic tug-of-war? Understanding the subtle properties and distribution of dark matter is crucial for refining our models of cosmic expansion and predicting the universe's ultimate fate. Even as we now know, there's another, more dominant force at play. It's a complex, beautiful puzzle, gently inviting us to understand the subtle wisdom of cosmic composition and its profound gravitational embrace. So, as you continue to drift, allow your mind to gently contemplate how matter softly pulls back through the pervasive, subtle embrace of gravity, seeking to decelerate the universe's outward journey. Feel the profound peace that comes from understanding this long-held cosmic expectation, this harmonious balance between expansion and gravitational pull, guiding the grand, unhurried rhythm of the universe. Let this understanding cradle your consciousness, like the serene, unwavering presence of cosmic gravity, as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of cosmic deceleration, a testament to the universe's profound self-regulation, is now your lullaby, a soft reassurance that wonder and mystery exist even in the familiar embrace of cosmic gravity, always inviting us to explore the subtle forces that shape our grand cosmos. You're floating deeper now, gently carried by the quiet understanding of matter's gentle pull, which once seemed destined to slow the universe's grand expansion. As you drift, let's turn our gaze to the subtle whispers that first revealed a profound cosmic surprise, a discovery that quietly reshaped our understanding of the universe's ultimate fate. Imagine light, those ancient, patient travelers from distant galaxies, carrying a secret message across unimaginable cosmic distances, revealing a truth that defied all expectations. This is the serene essence of the distant light of galaxies, a cosmic beacon whispering of a universe expanding faster than it should, revealed by the subtle, beautiful phenomenon of redshift. For much of the 20th century, cosmologists diligently observed the universe, meticulously charting the movements of distant galaxies. They expected to see these galaxies receding from us, a natural consequence of the universe's expansion from its hot, dense, early state. However, they anticipated that this recession would be subtly slowing down over cosmic time, gently pulled back by the collective gravitational embrace of all the matter and energy within the cosmos. Much like a ball thrown upward eventually decelerates due to Earth's gravity. The big question was whether this deceleration would be enough to eventually stop the expansion, or even reverse it. But then, in the late 1990s, a quiet revolution began to unfold. Astronomers, using the most powerful telescopes and delicate instruments, embarked on a patient quest to measure the expansion rate of the universe with unprecedented precision. Their method relied on observing the light from incredibly distant celestial objects, particularly a special type of exploding star called a Type Ia supernova. Imagine these Types Ia supernovae as cosmic standard candles. Think of them like perfectly identical, exquisitely crafted light bulbs, each one burning with precisely the same inherent brightness, no matter where it is in the universe. When one of these rare, brilliant stars explodes in a distant galaxy, it produces a temporary burst of light so intense that it can briefly outshine an entire galaxy. Because scientists understood the precise intrinsic brightness of these standard candles, they could measure how bright they appeared from Earth. The dimmer they appeared, the further away they must be. Much like a familiar flashlight appears fainter the further it is carried into the quiet night. Now, here's where the subtle whisper of the universe's secret began to emerge. As light from these distant supernovae traveled across billions of light-years of expanding space, its wavelengths were gently stretched. Imagine a long, soft piece of elastic with a wave drawn on it. As you slowly stretch the elastic, the wave itself gets longer, its crests and troughs moving further apart. Similarly, as space expands, the wavelengths of light traveling through it are gently stretched, causing them to shift towards the redder end of the spectrum. This phenomenon is known as cosmological redshift. The more the light is redshifted, the more space has expanded since that light left its source, and therefore, the further away and earlier in cosmic time that supernova exploded. Scientists meticulously measured the redshift of countless distant Type Ia supernovae, using this information to calculate their distance and, by extension, the rate at which the universe was expanding at different points in cosmic history. They expected to see evidence of deceleration, that the more distant and thus older supernovae would show a slightly faster rate of recession, because the expansion was stronger in the early universe before gravity had much time to slow it down. But the results, when they gently unfurled from the data, were astonishingly different. Instead of slowing down, the data from these distant cosmic beacons quietly revealed that the universe's expansion was actually accelerating. The more distant supernovae appeared fainter than they should have been if the universe's expansion was decelerating. This meant that the space between us and those ancient explosions was stretching faster now than it was in the past. It was like throwing that pebble upwards, expecting gravity to slow it down, only to find it subtly speeding up as it ascended, as if an unseen, gentle hand were continuously pushing it from below. This profound cosmic surprise challenged decades of cosmological expectation and opened up an entirely new chapter in our understanding of the universe. This discovery was so profound, so unexpected, that it earned the Nobel Prize in Physics in 2011 for the 3 astronomers who independently led the teams that made this gentle revelation. It meant that something mysterious, something profound, was at work in the cosmos, subtly overcoming the gravitational pull of all the matter and energy, and instead causing space itself to stretch at an ever-increasing rate. This unseen, pervasive force, this quiet accelerator of cosmic destiny, was given a fittingly enigmatic name: dark energy, a general historical fact that highlights the significance of this discovery. Before the discovery of accelerated expansion, the ultimate fate of the universe was a binary choice. Either it would eventually contract in a big crunch, or expand forever at an ever-slowing rate, the big chill. The revelation of accelerated expansion introduced a new, dominant scenario, the Big Freeze, or heat death, where the universe continues to expand, becoming colder and more dilute, forever. This profoundly altered our cosmic predictions. Here's a lesser-known detail about Type Ia supernovae as standard candles. These particular supernovae are so useful because they are thought to explode when a white dwarf star, the dense remnant of a sun-like star, accretes matter from a companion star, eventually reaching a critical mass, the Chandrasekhar limit, before exploding. This consistent explosion mechanism leads to a very uniform peak brightness, making them exceptionally reliable for measuring cosmic distances across vast stretches of time and space. It's like a quiet, perfectly calibrated flashbulb, appearing consistently across the cosmos, and for an ongoing academic debate. While the accelerating expansion is now widely accepted based on multiple lines of evidence, the precise nature of dark energy remains one of the greatest mysteries in modern physics. Is it a constant, cosmological constant, a property of empty space itself, subtly pushing space apart? Or is it a more dynamic, evolving quintessence field, subtly changing its properties over cosmic time? Scientists are patiently gathering more data and exploring new theories to gently unravel the enigma of this pervasive, unseen cosmic accelerator, revealing the subtle wisdom of reality's grandest and most surprising forces. So, as you continue to drift, allow your mind to gently contemplate the distant light of galaxies, carrying ancient secret messages across cosmic distances. Feel the profound peace that comes from understanding how these gentle beacons revealed a universe expanding faster than it should. challenging our expectations and opening new doors of cosmic wonder. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of light traveling through expanding space, as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of an accelerating universe, a testament to cosmic surprises, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, forever guiding us towards the serene future. Now, let's deepen our gentle understanding of this profound cosmic revelation by considering the meticulous process through which these distant whispers of light are collected and interpreted. Imagine the vast, dark expanse between galaxies, not as empty space, but as a colossal, transparent canvas through which the light from ancient explosions patiently travels. To capture these faint, distant signals, astronomers use not just any telescope, but immense, sophisticated instruments, often located in remote, high-altitude deserts or even drifting silently in the quiet vacuum of space. These colossal telescopes, whether nestled on mountaintops or orbiting Earth, act like giant, patient eyes, gathering every precious photon of light that has journeyed across billions of light years. The mirrors are meticulously polished to near perfection, reflecting the faintest glimmer from the edge of the observable universe. Once collected, this light is then directed to incredibly sensitive detectors and spectrographs. These instruments don't just capture an image, they delicately spread the light into its constituent wavelengths, much like a prism gently separates white light into a rainbow. Each subtle shift in the color of this cosmic rainbow, particularly towards the red end of the spectrum, becomes a precise measurement of that galaxy's recession speed, and, by extension, how much the space between us and it has stretched. The sheer volume of data collected is immense. Imagine countless individual supernovae, each a unique, fleeting cosmic event, providing a single data point. Astronomers, like diligent cosmic cartographers, then meticulously plot these points on a grand chart, comparing their apparent brightness, which indicates distance, to their redshift, which indicates recession speed. When these points are plotted across billions of light years, a clear, unmistakable pattern emerges the further away the supernovae are meaning, the further back in cosmic time their light originated, the slower the universe was expanding when their light began its journey. This subtle curve in the expansion history, a quiet deviation from the expected straight line of deceleration, was the undeniable proof of acceleration. Consider the profound implications of this method. It's like standing on a gentle riverbank, and by observing how fast tiny, distant leaves are floating away, and how their colors subtly change as they drift, you can deduce that the river itself, far from your immediate view, is actually speeding up its flow over vast stretches of its course. The precision required for such measurements, correcting for subtle factors like dust absorption within distant galaxies or the slight intrinsic variations between supernovae, is a testament to the quiet dedication and ingenious methods of modern cosmology. This constant refinement of measurement techniques is crucial. The initial discovery of acceleration, while revolutionary, spurred further efforts to confirm it with even greater precision. Scientists have used other cosmic standard rulers, like the subtle imprints of sound waves from the early universe in the cosmic microwave background radiation, to independently measure the expansion rate. The consistent agreement across these diverse methods, despite the subtle Hubble tension we will explore later, reinforces the profound reality of accelerated expansion, a quiet symphony of independent cosmic observations harmonizing to reveal a deeper truth, a general historical fact that emphasizes the elegance of redshift measurement. The concept of redshift was first described by Christian Doppler in the 19th century for sound waves' Doppler effect, and later adapted by astronomers like Vesto Slipher and Edwin Hubble for light waves. Their early measurements of galactic redshifts laid the fundamental groundwork for understanding cosmic expansion, long before the precision instruments of today could reveal the subtle acceleration. Here's a lesser-known detail about the cosmic distance ladder. The accuracy of the Type Ia supernova measurements relies heavily on the rung below them. On the ladder, the Cepheid variable stars. These stars, while predictable, can be subtly affected by their metallicity, the abundance of heavier elements in their composition, which can slightly alter their brightness period relationship. Astronomers meticulously account for these subtle variations, constantly refining their calibration to ensure the most precise distance measurements possible. It's like a quiet craftsman, endlessly sharpening their tools to achieve the most delicate cuts. And for an ongoing academic debate, one of the key areas of active research is the calibration of the entire cosmic distance ladder, from nearby stars to the most distant supernova. Are there any subtle, systematic biases in our current measurements that might account for some of the Hubble tension, that slight disagreement between early and late universe measurements of the expansion rate? Scientists are patiently working to eliminate all potential sources of systematic error, ensuring that their cosmic speedometer is as exquisitely precise as possible, always seeking the most accurate whisper from the universe about its true rate of expansion. So, as you continue to drift, allow your mind to gently contemplate the distant light of galaxies, carrying ancient, secret messages across cosmic distances. Feel the profound peace that comes from understanding how these gentle beacons revealed a universe expanding faster than it should, challenging our expectations and opening new doors of cosmic wonder. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of light traveling through expanding space, as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of an accelerating universe, a testament to cosmic surprises, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, forever guiding us towards the serene future. You're floating deeper now, gently carried by the quiet understanding of distant starlight, whispering of a universe expanding faster than it should. As you drift, let's turn our gaze to the subtle messengers that first unveiled this profound cosmic surprise. Those luminous beacons that allowed us to measure the universe's accelerating rhythm. Imagine tiny, ancient stars, having lived their lives in distant galaxies, now reaching their final, magnificent moments, erupting in a brilliance so uniform, so predictable, that they become cosmic measuring tapes across the vastness. This is the serene essence of unexpected smiles from eternal darkness. How supernovae, in their quiet, majestic explosions, gently revealed the universe's most profound secret, shining like perfect, cosmic candles. For centuries, astronomers dreamed of a way to accurately measure the immense distances to the farthest reaches of the universe. Without knowing how far away a galaxy was, it was impossible to truly understand how fast it was moving away from us due to expansion, or how that expansion rate was changing over cosmic time. The light from distant galaxies, while carrying the signature of redshift space stretching its wavelengths, didn't inherently tell us their distance. It was like trying to guess the size of a faraway boat just by seeing its blurry silhouette. We needed a cosmic ruler, a universal, standard candle, whose true brightness was known. And then, scientists gently discovered these perfect cosmic measuring tools. Type Ia supernovae. Imagine a very specific kind of star, often a dense, ancient remnant of a sun-like star called a white dwarf. These white dwarfs, incredibly compact and massive, often exist in binary systems, quietly orbiting a companion star. Over immense stretches of time, the white dwarf patiently and subtly siphons off gas from its companion, like a gentle, invisible hand slowly drawing liquid from a nearby well. As it accumulates more and more mass, it eventually reaches a critical limit about 1.4 times the mass of our Sun, a threshold known as the Chandrasekhar limit. When the white dwarf gently crosses this precise mass limit, a profound and beautiful transformation occurs. The immense gravitational pressure in its core triggers a runaway thermonuclear explosion. This isn't a chaotic, messy burst. It's a remarkably consistent and incredibly powerful cosmic event, a thermonuclear detonation that consumes the entire white dwarf star in a flash of unimaginable brilliance. The beauty of Type Ia supernovae is their astonishing uniformity, because they all explode under almost identical conditions. They all reach approximately the same peak intrinsic brightness. It's like countless tiny, perfectly crafted flashbulbs, each one calibrated to emit precisely the same amount of light, scattered across the vast cosmic dark, patiently waiting to illuminate a secret. This uniformity makes them perfect standard candles. When a Type Ia supernova occurs in a distant galaxy, astronomers can measure how bright it appears from Earth. Since they know its true intrinsic brightness, the fainter it appears, the further away it must be. It's a simple, elegant principle, applied across billions of light years. Imagine countless identical lighthouses, shining with the same exact power. If one appears very dim, you know it's incredibly far away. If another appears brighter, it's closer. The apparent dimness becomes a precise measure of cosmic distance, allowing scientists to delicately map the universe's grand scale. In the late 1990s, two independent teams of astronomers embarked on a patient quest to use these Type Ia supernovae to measure the universe's expansion history. They expected to see a universe that was subtly decelerating, slowing down due to the gravitational pull of all its matter. So, the more distant and thus older supernovae should have appeared brighter than expected, as the universe was expanding slower in the past, meaning their light didn't have to travel through as much stretched space. But the data, when it gently unfurled from their meticulous observations, revealed a profound and utterly unexpected truth. Instead, the supernovae in the most distant galaxies appeared fainter than they should have been if the universe's expansion was slowing down. This could only mean one astonishing thing. The space between us and those ancient explosions was stretching faster now than it was in the past. The universe's expansion was not decelerating. It was, in fact, accelerating. It was as if, in our cosmic analogy of a ball thrown upwards, we expected gravity to slow it down, only to find it subtly speeding up as it ascended, propelled by an unseen, gentle push. This profound cosmic surprise, revealed by the quiet, predictable explosions of distant stars, challenged decades of cosmological expectation and opened up an entirely new chapter in our understanding of the universe. This discovery was so profound, so counterintuitive, and yet so beautifully consistent across independent observations that it fundamentally reshaped our understanding of cosmic destiny. It led to the inescapable conclusion that something mysterious, something pervasive, was at work in the cosmos, subtly overcoming the gravitational pull of all the matter and energy, and instead causing space itself to stretch at an ever-increasing rate. This unseen, pervasive force, this quiet accelerator of cosmic destiny, was given a fittingly enigmatic name: dark energy. The universe, in its boundless creativity, had revealed a new, silent player in its grand cosmic drama. A general historical fact that highlights the significance of this discovery: the independent discoveries of the accelerating universe, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, were so revolutionary that they were awarded the Nobel Prize in Physics in 2011. Their patient observations of Type Ia supernovae fundamentally changed our cosmological models and the predicted ultimate fate of the universe. Here's a lesser-known detail about Type Ia supernovae as standard candles. These particular supernovae are so useful because they are thought to explode when a white dwarf star, the dense remnant of a sun-like star, accretes matter from a companion star, eventually reaching a critical mass, the Chandrasekhar limit, before exploding. This consistent explosion mechanism leads to a very uniform peak brightness, making them exceptionally reliable for measuring cosmic distances across vast stretches of time and space. It's like a quiet, perfectly calibrated flashbulb, appearing consistently across the cosmos. And for an ongoing academic debate. While the accelerating expansion is now widely accepted based on multiple lines of evidence, the precise nature of dark energy remains one of the greatest mysteries in modern physics. Is it a constant, cosmological constant, a property of empty space itself, subtly pushing space apart? Or is it a more dynamic, evolving quintessence field, subtly changing its properties over cosmic time? Scientists are patiently gathering more data and exploring new theories to gently unravel the enigma of this pervasive, unseen cosmic accelerator, revealing the subtle wisdom of reality's grandest and most surprising forces. So, as you continue to drift, allow your mind to gently contemplate the unexpected smiles from eternal darkness, those supernovae that, in their quiet, majestic explosions, revealed the universe's profound secret. Feel the profound peace that comes from understanding how these gentle beacons illuminated a universe expanding faster than it should, challenging our expectations and opening new doors of cosmic wonder. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of light traveling through accelerating space, as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of an accelerating universe, a testament to cosmic surprises, is now your lullaby, a soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, forever guiding us towards the serene future. Now, let's deepen our gentle understanding of how these Type Ia supernovae, these perfect cosmic candles, are meticulously identified and used to paint the grand picture of the universe's accelerating expansion. Imagine countless galaxies scattered across the vast canvas of the cosmos, each a swirling island of stars. Within these galaxies, countless stars live and die, but only a tiny fraction will end their lives in the precise, uniform explosion of a Type Ia supernova. To find these rare, fleeting events, astronomers embark on a patient, continuous cosmic watch. They use wide-field telescopes to survey vast swaths of the night sky, patiently looking for new, sudden bursts of light that appear in distant galaxies where no such bright star was previously observed. Once a potential supernova is identified, multiple telescopes, sometimes from around the world, are quickly directed to its location. This rapid response is crucial because Type Ia supernovae reach their peak brightness relatively quickly, within a matter of days, and then gently fade over several weeks or months. It's like patiently searching a vast, silent forest for a rare, luminous flower that blooms only for a brief, magical period, requiring quick and coordinated observation to truly capture its essence. Once the light from these supernovae is captured, it undergoes meticulous analysis. Astronomers study their light curves, which are plots of how their brightness changes over time. For Type Ia supernovae, these light curves have a very distinct, predictable shape, a rapid rise to peak brightness, followed by a slower, consistent decline. This characteristic shape is another testament to their uniformity, ensuring they are truly Type Ia and can thus be used as reliable standard candles. Any deviation from this expected shape might indicate a different type of supernova or an interfering factor, and such observations are carefully excluded from the critical measurements. This careful vetting ensures the integrity of the profound cosmic revelation. The accuracy of these measurements relies not just on observing the supernova itself, but also on precisely measuring the redshift of its host galaxy. Remember, redshift is the stretching of light wavelengths as space expands, telling us how fast a galaxy is receding from us. By measuring the redshift of the galaxy where the supernova occurred, scientists get a precise measure of the expansion rate of space at the moment the light from that supernova was emitted. Comparing this ancient expansion rate with the supernova's apparent brightness, its distance, allowed astronomers to see that the universe's expansion was actually speeding up. It's like gently dropping countless pebbles into a vast, stretching pond. And by observing the final position and faded color of each ripple, you can deduce that the pond itself is mysteriously expanding faster now than it was when the pebbles first fell. This intricate process, from supernova discovery to light curve analysis and redshift measurement, requires immense scientific collaboration. Teams of astronomers, physicists, and cosmologists around the world share data, refine techniques, and meticulously check each other's work. This collective pursuit of knowledge, driven by a shared curiosity about the universe's deepest secrets, is a beautiful testament to the human spirit of cooperation. The profound conclusions drawn from these observations are not the result of a single brilliant insight, but of countless gentle steps, patiently taken by countless dedicated minds. A general historical fact that highlights the quiet technological leap before the late 20th century, finding and rapidly observing Type Ia supernovae was incredibly challenging. The development of automated sky surveys and rapid response robotic telescopes was crucial for detecting these transient events soon after they exploded, allowing astronomers to capture their peak brightness with the precision needed for cosmological measurements. Here's a lesser-known detail about the potential future of standard candles. Scientists are exploring other potential standard candles, or standard rulers, in the universe that could offer independent checks on the acceleration of expansion and the nature of dark energy. One promising candidate is gravitational waves from the merger of neutron stars, which can also act as standard sirens to measure cosmic distances. These new cosmic messengers promise to add new, subtle harmonies to the symphony of cosmic measurement, potentially offering even more precise insights into the universe's accelerating rhythm. It's like listening for a unique, almost imperceptible sound that can reveal new truths about the vastness, and for an ongoing academic debate. One of the biggest challenges in using Type Ia supernovae is accurately accounting for intervening dust in distant galaxies, which can subtly dim their light and make them appear fainter and thus further away than they truly are. Astronomers use various techniques to correct for this cosmic dust. But the precise accuracy of these corrections is still an area of active research and gentle debate, as even subtle errors could impact the measured acceleration rate and the ultimate conclusions about dark energy. It's a complex, beautiful puzzle, gently inviting us to understand the subtle wisdom of light's journey through the cosmos. So, as you continue to drift, allow your mind to gently contemplate the unexpected smiles from eternal darkness. Those supernovae that, in their quiet, majestic explosions, revealed the universe's profound secret. Feel the profound peace that comes from understanding how these gentle beacons illuminated a universe expanding faster than it should, challenging our expectations and opening new doors of cosmic wonder. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of light traveling through accelerating space, as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of an accelerating universe, a testament to cosmic surprises, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, forever guiding us towards the serene future. You're floating deeper now, gently carried by the quiet understanding of supernovae's unexpected smiles, revealing a universe expanding faster than it should. As you drift, let's turn our attention to the profound implications of this astonishing discovery, how the very flow of time and space, that relentless cosmic rhythm, appears to be subtly accelerating, driven by a mysterious, unseen force. Imagine a vast, serene river, its currents gently flowing towards a distant sea. But instead of gradually slowing, it begins to mysteriously quicken its pace, pulling everything along with it at an ever-increasing speed. This is the serene essence of time's quietly accelerated flow, where the universe's grand expansion is subtly being pushed, hinting at profound new layers of cosmic understanding. For billions of years after its quiet dawn, the universe expanded. And for most of cosmic history, it was expected that this expansion would be slowing down. The collective gravitational pull of all the matter and energy within the cosmos was thought to act like a pervasive, gentle anchor, subtly decelerating the outward rush of space, much like gravity gradually slows down a ball thrown upwards. This expected deceleration was a cornerstone of cosmological thought, a harmonious balance between the initial outward push of the Big Bang and the relentless inward pull of all that exists. However, the profound revelations from observing distant Type Ia supernovae, those perfect cosmic candles, shattered this long-held expectation. The data, gently unfurling from meticulous observations, unequivocally showed that the universe's expansion was not decelerating, but was, in fact, accelerating. This meant that the space between galaxies was stretching faster now than it was in the past, as if an unseen, gentle hand were continuously pushing the cosmic fabric outwards with ever-increasing vigor. This quiet acceleration was a profound cosmic surprise, one of the most significant discoveries in cosmology in decades. This unexpected acceleration led to the inescapable conclusion that something mysterious, something pervasive, was at work in the cosmos, subtly overcoming the gravitational pull of all the visible matter, the dark matter, and all other known forms of energy. This enigmatic force, subtly pushing space apart at an ever-increasing rate, was given the evocative name of dark energy. Imagine it not as a chaotic, explosive force, but as a subtle, pervasive pressure, an inherent property of space itself that gently pushes everything outwards, causing the very fabric of the cosmos to swell with increasing speed. It's like a quiet, invisible breath, continuously inflating the grand balloon of the universe with an ever-increasing subtlety. The nature of this dark energy is one of the greatest mysteries in modern physics, a profound cosmic puzzle that physicists are patiently striving to unravel. One leading idea is that dark energy is a cosmological constant, a concept first proposed by Albert Einstein himself, almost a century ago, as a subtle modification to his equations of general relativity. Imagine it as an intrinsic property of empty space, a constant uniform energy density that subtly generates a repulsive gravitational force, causing space to expand. If this is true, then as space expands, more empty space is created, and thus more dark energy, leading to a self-reinforcing cycle of accelerating expansion. It's like a vast, serene ocean that, as it grows larger, produces more of the very water that causes it to expand. Another intriguing idea is that dark energy is not a constant, but a dynamic, evolving field, sometimes referred to as quintessence. Imagine it as a subtle, pervasive cosmic fluid, or a slowly shifting energy field, whose properties and strength might change over cosmic time. If this were true, the rate of acceleration might also change, perhaps subtly increasing or decreasing for eons, leading to different ultimate fates for the universe. This concept introduces an additional layer of elegant complexity to the cosmic ballet, hinting at a universe that is even more fluid and dynamic than we currently comprehend. The implications of this accelerating expansion are profound, dramatically reshaping our understanding of the universe's ultimate destiny. Instead of an eventual big crunch or a perpetually but slowly expanding big chill, the accelerating expansion points towards a future where the universe continues to grow, becoming ever colder, ever more dilute, and ever more isolated. Galaxies will drift further and further apart, their light eventually dimming and redshifting beyond detection, leaving each galaxy as a lonely island in a vast, cold, dark, and silent cosmic sea. This is the scenario often referred to as the Big Freeze or heat death of the universe, a profound, unhurried dissolution into ultimate stillness. A general historical fact that neatly highlights the intellectual journey toward dark energy. The concept of a cosmological constant was originally introduced by Einstein to force his equations to describe a static universe, a notion he later called his biggest blunder after Edwin Hubble discovered cosmic expansion. The rediscovery of accelerated expansion in the late 1990s, however, resurrected Einstein's cosmological constant as a leading candidate for dark energy, showing how a seemingly mistaken idea can find new, profound relevance in an evolving cosmic landscape. Here's a lesser-known detail about the subtle effects of dark energy. While dark energy causes space to expand at an accelerating rate on the largest cosmic scales, its influence is incredibly weak on smaller scales. It does not overcome gravity within galaxies or solar systems. This means that your cozy home, our gentle Earth, and even our familiar Milky Way galaxy will remain intact, held together by the gentle embrace of gravity. Even as the vast space between galaxies stretches ever faster due to the unseen push of dark energy, it's like a quiet, invisible breath that can inflate an entire balloon, but has no effect on the tiny dots painted on its surface. And for an ongoing academic debate, physicists are still actively researching the precise nature of dark energy and whether its properties are truly constant over cosmic time. Are there subtle variations in its strength, or is it fundamentally unchanging? The precise nature of dark energy is not only crucial for predicting the universe's ultimate fate, but also for understanding the fundamental laws of physics at their most extreme limits. This intricate and beautiful puzzle At the intersection of cosmology and fundamental particle physics remains one of the most fascinating and complex areas of study, revealing the subtle wisdom of reality's grandest and most surprising forces. So, as you continue to drift, allow your mind to gently contemplate time's quietly accelerated flow, feeling the profound peace that comes from understanding how the universe's grand expansion is subtly being pushed by a mysterious, unseen force. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of an expanding cosmos, gently stretching and accelerating as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of dark energy, a testament to cosmic surprises and hidden forces, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, forever guiding us towards the serene future. Now, let's deepen our gentle understanding of this enigmatic dark energy by considering how it subtly shapes the very fabric of space-time, not by pulling it together like gravity, but by causing it to gracefully stretch. Imagine space-time as a vast, infinitely thin cosmic dough. Gravity, from matter and dark matter, acts like a subtle indentation, creating localized dips and wells where galaxies and clusters gently gather. Dark energy, however, is woven into the very consistency of the dough itself, causing it to uniformly and gently swell everywhere, subtly pushing these indentations further apart. This fundamental difference in how it interacts with spacetime makes it a profoundly unique and mysterious component of our universe. The very concept of a universe with an accelerating expansion suggests that the future is not just vast, but also increasingly isolated. If dark energy continues its gentle, pervasive push, eventually, distant galaxies will not only recede from us, but the light they emit will become so incredibly stretched, so profoundly redshifted, that it will shift beyond the observable spectrum, effectively disappearing from view. This means that future astronomers, perhaps trillions of years from now, would see a night sky that is almost entirely empty, save for their own local cluster of galaxies. This quiet cosmic isolation, a direct consequence of accelerated expansion, paints a serene, yet profound picture of cosmic solitude. This accelerating expansion also has subtle implications for the formation of structures in the universe. While gravity has successfully pulled matter together to form galaxies and clusters of galaxies over billions of years, the relentless push of dark energy on the grandest scales means that no new large-scale structures will be able to form in the far distant future. Any new clumps of matter would be gently pulled apart by the accelerating expansion before they could gather enough mass to overcome the cosmic push. So, the universe, in its future, will be one where existing structures continue their isolated dance, but where the grand process of cosmic construction on large scales has subtly ceased. Consider the profound patience of these cosmic processes. The acceleration is not a dramatic, sudden burst, but a continuous, gentle increase in the expansion rate, unfolding over timescales that make the current age of the universe seem like a mere fleeting moment. This unhurried nature allows for the subtle interplay of forces to play out with exquisite precision, guiding the cosmos towards its ultimate destiny with a serene, inevitable grace. The universe, in its boundless wisdom, is not rushing. It is simply flowing along its most probable path, guided by the unseen hand of dark energy. A general historical fact that highlights the subtlety of dark energy. Despite its profound influence on the fate of the universe, dark energy is incredibly diffuse. Its energy density is extremely low, far lower than the density of matter or even dark matter in our local cosmic neighborhood. This means its effects are only observable on the very largest cosmic scales, spanning billions of light years. In our everyday experience, its influence is utterly negligible, a testament to its pervasive, yet incredibly subtle, nature. Here's a lesser-known detail about the potential origin of dark energy. Some speculative theories gently propose that dark energy might be related to fundamental quantum fluctuations in the vacuum of space, constantly popping into and out of existence. While this idea has its own profound challenges predicting a far greater energy density than observed, it hints at a deep connection between the smallest, most ephemeral aspects of quantum reality and the largest, most pervasive force shaping the cosmos. It's like a quiet, hidden hum from the very fabric of existence, subtly influencing the grandest cosmic movements. And for an ongoing academic debate, physicists are still actively researching whether dark energy's properties are truly constant over cosmic time, as implied by the cosmological constant, the simplest model, or if they are subtly changing. If dark energy were to strengthen significantly over time, it could lead to an even more dramatic and profound end for the universe. The Big Rip, where the acceleration becomes so extreme that it tears apart not just galaxies, but stars, planets, and even atoms themselves, in a final, gentle unraveling. Understanding the exact nature of dark energy, its subtle evolution, and its ultimate impact on the cosmos remains a fascinating and complex area of study, revealing the subtle wisdom of reality's grandest and most surprising forces. So, as you continue to drift, allow your mind to gently contemplate time's quietly accelerated flow, feeling the profound peace that comes from understanding how the universe's grand expansion is subtly being pushed by a mysterious, unseen force. Let this understanding cradle your consciousness like the serene, unwavering rhythm of an expanding cosmos, gently stretching and accelerating as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of dark energy, a testament to cosmic surprises and hidden forces, is now your lullaby, a soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, forever guiding us towards the serene future, filled with boundless curiosity and gentle cosmic puzzles yet to be unraveled. You're floating deeper now, gently carried by the quiet understanding of time's quietly accelerated flow, feeling the subtle push of dark energy. As you drift, let's turn our attention to how our deepest theories about the universe, those elegant mathematical frameworks, are gently challenged and expanded by this profound mystery. Imagine a beautifully crafted, ancient map of the world, meticulously drawn with all known lands and seas, suddenly revealing a vast, uncharted ocean, filled with unseen currents and unexpected depths. This is the serene essence of where cosmic laws meet new mysteries, how the accelerating expansion of the universe pushes the boundaries of our understanding, inviting a humble re-evaluation of the very fabric of physical reality. For centuries, our understanding of the universe has been built upon pillars of elegant physical laws. Newton's gentle laws of motion and gravity beautifully explained the dance of planets around the sun. Later, Einstein's profound theory of general relativity reshaped our understanding of gravity itself, describing it as the curvature of spacetime, and elegantly predicted a universe that could expand or contract. These theories, meticulously tested and observed, provided a comforting sense of predictability and order to the cosmos. They were our guiding lights, illuminating the vast stretches of cosmic history. However, The discovery of the universe's accelerating expansion introduced a profound yet gentle challenge to these established frameworks. Before this discovery, the universe's expansion was expected to be slowing down due to the attractive force of gravity exerted by all matter and energy. The acceleration meant that there had to be something else, something pervasive and repulsive, subtly pushing space apart. This unknown entity, this cosmic enigma, was named dark energy. Its existence suggests that our current understanding of the universe's fundamental components and its governing laws, while incredibly powerful, might be incomplete, like a beautifully composed symphony missing a vital, underlying bass note. The simplest explanation for dark energy is Einstein's cosmological constant, a term he once introduced into his equations to describe a static universe before expansion was discovered, and later famously called his biggest blunder. Imagine it as an intrinsic property of empty space itself, a constant energy density woven into the very fabric of space-time, subtly generating a repulsive gravitational effect that pushes space apart. If this is true, then as space expands, more empty space is created, and thus more cosmological constant, leading to a self-reinforcing cycle of accelerating expansion. The elegance of this idea lies in its simplicity, but it also raises profound questions. Why does empty space have this particular amount of energy? And why is it precisely the right amount to cause the observed acceleration? It's like discovering that the very air you breathe has a subtle, inherent power to gently push you forward. A profound and unexpected property. Another intriguing theoretical idea is that dark energy is not a constant, but a dynamic, evolving field, sometimes referred to as quintessence. Imagine it as a subtle, pervasive cosmic fluid, or a slowly shifting energy field whose properties and strength might change over cosmic time. If this were true, the rate of acceleration might also change, perhaps subtly increasing or decreasing over eons, leading to different ultimate fates for the universe than currently envisioned. This concept introduces an additional layer of elegant complexity to the cosmic ballet, hinting at a universe that is even more fluid and dynamic than we currently comprehend. These theories, while attempting to explain dark energy, gently push the boundaries of our existing cosmic laws. They compel physicists to explore new avenues of research, to refine their mathematical models, and to seek subtle new insights into the fundamental nature of space, time, and gravity itself. The accelerating expansion is a quiet invitation from the cosmos, urging us to look deeper, to listen more closely to its subtle whispers, and to expand our understanding of its most profound mechanisms. It's like a beautifully crafted lock, where one key, the accelerating expansion, doesn't quite fit, hinting at a hidden tumbler or a new, subtle way of turning that will unlock even grander chambers of cosmic wisdom. The profound implications of dark energy extend to the very early universe. Could its properties be subtly linked to the initial conditions of the Big Bang, or to the very brief, rapid inflation period that is thought to have smoothed out the early cosmos? Understanding dark energy is not just about the universe's distant future. It's about comprehending its profound origins and the fundamental forces that have guided its entire journey. This intricate connection between the smallest whispers of cosmic beginnings and the largest, accelerating expansions of cosmic destiny, highlights the seamless unity of universal laws across all scales of time and space, a general historical fact that highlights the humbling nature of scientific discovery. The discovery of dark energy, arguably the most significant cosmological discovery since the expansion of the universe itself, occurred entirely by surprise. It was not predicted by existing models, demonstrating that even with our most elegant theories, the universe can still hold profound, unexpected secrets, patiently waiting to be revealed through meticulous observation. This reminds us that humility and openness are vital companions on the path of scientific understanding. Here's a lesser-known detail about the subtle effects of dark energy. While dark energy's influence is dominant on the largest cosmic scales, causing galaxies to accelerate away from each other, its effect on smaller scales is incredibly minute. It does not overcome the gentle gravitational embrace within galaxies or solar systems. This means that your cozy home, our gentle Earth, and even our familiar Milky Way galaxy will remain intact, held together by the gentle embrace of gravity, even as the vast space between galaxies stretches ever faster due to the unseen push of dark energy. It's like a quiet, invisible breath that can inflate an entire balloon, but has no effect on the tiny dots painted on its surface. And for an ongoing academic debate, scientists are still actively researching the precise nature of dark energy and whether its properties are truly constant over cosmic time. Are there subtle variations in its strength, or is it fundamentally unchanging? The precise nature of dark energy is not only crucial for predicting the universe's ultimate fate, but also for understanding the fundamental laws of physics at their most extreme limits. This intricate and beautiful puzzle, at the intersection of cosmology and fundamental particle physics, remains one of the most fascinating and complex areas of study, revealing the subtle wisdom of reality's grandest and most surprising forces. So, as you continue to drift, allow your mind to gently contemplate where cosmic laws meet new mysteries, feeling the profound peace that comes from understanding how the accelerating expansion of the universe pushes the boundaries of our knowledge. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of an expanding cosmos, gently stretching and accelerating as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of dark energy, a testament to cosmic surprises and hidden forces, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, forever guiding us towards the serene future, filled with boundless curiosity and gentle cosmic puzzles yet to be unraveled. Now, let's allow our minds to delve even deeper into the subtle, profound implications of this accelerating universe, exploring how the very presence of dark energy encourages us to reconsider what we thought were settled truths about the cosmos. Imagine our universe as a perfectly balanced, grand cosmic scale, where the weight of matter and energy on one side was thought to perfectly predict its future movements. The discovery of dark energy is like finding an invisible, gentle feather constantly adding weight to one side, slowly but surely, tipping the balance in an unexpected direction. This unexpected acceleration suggests that the universe's future is not just vast, but also increasingly solitary. If dark energy continues its gentle, pervasive push, eventually, distant galaxies will not only recede from us, but the light they emit will become so incredibly stretched, so profoundly redshifted, that it will shift beyond the observable spectrum, effectively disappearing from view. This means that future astronomers, perhaps trillions of years from now, would see a night sky that is almost entirely empty, save for their own local cluster of galaxies. This quiet cosmic isolation, a direct consequence of accelerated expansion, paints a serene, yet profound picture of cosmic solitude, urging us to cherish the vibrant, interconnected cosmos we currently observe. The very existence of dark energy also gently pushes us to explore what lies beyond our current understanding of the Standard Model of particle physics. While the Standard Model beautifully describes the fundamental particles and forces that make up all known matter, it does not currently offer a natural explanation for a pervasive, repulsive force like dark energy. This means that if dark energy truly is a cosmological constant, it hints at a deeper, underlying structure of space-time or a fundamental energy inherent in the vacuum that we don't yet comprehend. If it's a dynamic field like quintessence, it implies the existence of new, previously undiscovered fundamental fields in the universe. These are not minor adjustments. They are profound invitations to expand the very foundational principles of physics, searching for new, gentle harmonies in the symphony of reality. Consider the cosmological principle, a foundational assumption in cosmology that states the universe is, on large scales, homogeneous looks the same everywhere, and isotropic looks the same in all directions. The observation of accelerated expansion and the assumption that dark energy is smoothly distributed throughout space generally supports this principle. However, if dark energy were to be clumpy or unevenly distributed, it could subtly challenge our understanding of this fundamental cosmic uniformity. The very smoothness of the accelerating expansion itself is a gentle confirmation of the universe's pervasive, elegant order on the grandest scales, a general historical fact that highlights the humility in scientific progress. The history of science is filled with instances where a seemingly small discrepancy or an unexpected observation led to a revolutionary shift in understanding. From the subtle wobble in Uranus's orbit that led to the discovery of Neptune, to the tiny anomalies in Mercury's orbit that confirmed Einstein's general relativity, the universe often reveals its deepest secrets through its gentle, unexpected whispers, inviting closer, patient attention, and ultimately leading to profound new insights. Here's a lesser-known detail about the potential for cosmic bounce or rebound theories. While the Big Freeze is currently the leading scenario, some highly speculative theories, gently explored by theoretical physicists, propose that dark energy might not remain forever dominant. Could its properties subtly change in the far-distant future, perhaps even causing it to become attractive, or leading to a big bounce where the universe eventually contracts again, but in a way that avoids a singularity? These are the delicate, whispered possibilities that arise at the very edge of our understanding, inviting boundless contemplation. It's like a quiet dream, exploring countless alternate realities in the stillness of the night. And for an ongoing academic debate, cosmologists are still actively researching the coincidence problem of dark energy. Why is dark energy only becoming dominant now, in the relatively recent cosmic past, after billions of years when matter and radiation dominated? Why are its energy density and the energy density of matter so remarkably similar in the present epoch? Seemingly a profound coincidence. Does this coincidence hint at a deeper underlying mechanism that subtly links dark energy to matter? Or is it simply a fortunate happenstance of cosmic timing? This intricate and beautiful puzzle remains one of the most fascinating and complex areas of study, revealing the subtle wisdom of reality's grandest and most surprising forces. So, as you continue to drift, allow your mind to gently contemplate where cosmic laws meet new mysteries, feeling the profound peace that comes from understanding how the accelerating expansion of the universe pushes the boundaries of our knowledge. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of an expanding cosmos, gently stretching and accelerating as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of dark energy, a testament to cosmic surprises and hidden forces, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most familiar corners of our cosmic tapestry, forever guiding us towards the serene future, filled with boundless curiosity and gentle cosmic puzzles yet to be unraveled. You're floating deeper now, gently carried by the quiet understanding of how cosmic laws meet new mysteries, revealing the profound influence of dark energy. As you drift, let's expand our contemplation to the grand, ethereal canvas of the universe's distant future. As subtly shaped by this accelerating expansion, imagine not a dramatic endpoint, but a serene, unhurried unfolding, where galaxies drift ever further apart, their lights softly fading into an immense, profound quietude. This is the serene essence of the universe's quiet, expansive future, where its boundless journey gracefully leads to an ultimate state of cold, dark, and tranquil solitude. For much of cosmology's history, the ultimate fate of the universe was a profound question, with competing, yet equally grand, scenarios. Would the universe eventually succumb to the gravitational embrace of its own matter, gently contracting back into a dense, primordial state, perhaps leading to a big crunch? Or would it expand forever, but at an ever-slowing pace, gradually fading into a big chill where stars eventually die out and the cosmos becomes a cold, dark stillness? These were the grand cosmic narratives, each holding its own poetic beauty. However, the discovery of the universe's accelerating expansion, driven by the enigmatic dark energy, dramatically reshaped these predictions. The gentle, pervasive push of dark energy subtly overcomes the attractive pull of gravity on the largest cosmic scales, ensuring that the expansion of space will not slow down, but instead continue to accelerate, perpetually increasing its pace. This profound revelation points towards a distinct and profoundly serene ultimate destiny for our cosmos, often referred to as the Big Freeze or the heat death of the universe. Imagine this far-distant future unfolding with an immense, unhurried grace. Over trillions upon trillions of years, stars, having lived their long, luminous lives, will eventually exhaust their nuclear fuel. Their brilliant fires will softly fade, one by one, into the cosmic twilight, leaving behind cold, dark remnants, white dwarfs, neutron stars, and black holes. The birth of new stars will become increasingly rare, as the gas and dust needed to form them will be stretched further and further apart by the accelerating expansion, making it harder for gravity to gently coax them together. It's like a colossal, ancient garden, where the vibrant flowers eventually complete their cycle, and the seeds, though still present, are scattered too widely to easily find new soil. As the eons pass, galaxies, those magnificent islands of stars, will continue to drift further and further apart from each other. The vast space between them will stretch and swell at an ever-increasing rate, ensuring that eventually, each galaxy will become a lonely, isolated entity, its light from other galaxies redshifted beyond detection. From within our own gentle Milky Way, if humanity still existed, the view of the night sky would profoundly change. Distant galaxies would appear dimmer and redder, eventually fading from view, until our local group of galaxies would be the only cosmic structures visible, surrounded by an immense, silent, and ever-expanding void. It's like watching countless tiny boats drifting further and further apart on an endlessly growing, silent ocean, until each becomes a solitary speck on the horizon, their lights no longer visible to one another. Even black holes, Those profound gravitational wells that endure for unimaginable stretches of time will not be eternal in this accelerating universe. Over quadrillions upon quadrillions of years, they too are predicted to slowly, imperceptibly evaporate through the gentle emission of Hawking radiation, releasing their stored energy back into the vast, cold cosmos. Their final whispers will echo into the void, leaving behind nothing but a diffuse sea of fundamental particles and a profound, pervasive stillness. In this ultimate scenario of the Big Freeze, entropy, that measure of disorder and energy dispersal, would have reached its absolute maximum. All the energy in the universe would be perfectly and uniformly spread out, evenly diffused across an infinitely vast, cold, and dark cosmos. There would be no more temperature differences to drive any processes, no more concentrated pockets of energy to fuel new stars or new life, no more discernible patterns or distinctions. All matter would be broken down into its most fundamental, dispersed forms, endlessly drifting in a state of absolute, profound equilibrium. It's like a single, perfect drop of vibrant color that has, over unimaginable stretches of time, finally diffused throughout an entire, boundless ocean, leaving no discernible pattern, just a uniform, serene blend. This state of ultimate entropy is not dramatic. It is one of profound, absolute stillness and quietude, a universe at perfect, unmoving rest. This vision of the universe's quiet, expansive future, while stretching beyond any human comprehension of time or scale, is not meant to inspire unease. Instead, it offers a profound, almost meditative, perspective on the fundamental laws that govern our universe. It reminds us that the second law of thermodynamics, entropy's gentle unfurling, is an overarching principle, a cosmic choreographer that orchestrates the grand ballet of existence from beginning to end. It is a testament to the universe's inherent tendency towards greater simplicity and blending, a peaceful surrender to the most probable state, a universe gracefully completing its vast, unhurried journey, a general historical fact that highlights the quiet revolution in cosmic predictions. Before the discovery of dark energy and accelerated expansion, the ultimate fate of the universe was often presented as a choice between a big crunch, recollapse, or a big chill, ever-slowing expansion. The revelation of accelerated expansion in the late 1990s dramatically shifted the consensus towards the Big Freeze, or heat death scenario, profoundly altering our cosmic predictions and our understanding of the universe's ultimate destiny. Here's a lesser-known detail about the profound quiet of this future. As galaxies drift far beyond each other's cosmic horizons, and their lights redshift out of visibility, any future civilizations that might exist would eventually experience a universe that appears largely empty, with only their local galaxy group visible. This would fundamentally change their understanding of cosmology, as the evidence for cosmic expansion and the existence of other galaxies would have largely vanished from their observable universe. It's like a quiet, cosmic library, where many of its grandest stories have gently receded beyond legible sight. And for an ongoing academic debate, cosmologists are still actively debating the precise parameters of dark energy, specifically whether its density will remain perfectly constant or subtly change over vast stretches of cosmic time. If dark energy were to strengthen significantly, it could lead to an even more dramatic end: the Big Rip, where the acceleration becomes so extreme that it tears apart not just galaxies, but stars, planets, and even atoms themselves. Understanding the exact nature of dark energy is key to fine-tuning our predictions for the universe's most profound and beautiful final secret, a complex and beautiful puzzle, gently inviting us to understand the subtle wisdom of reality's grandest rhythms. So, as you continue to drift, allow your mind to gently contemplate the universe's quiet, expansive future, feeling the profound peace that comes from understanding how its boundless journey gracefully leads to an ultimate state of cold, dark, and tranquil solitude. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of cosmic expansion itself, gently stretching and accelerating as you gently surrender to the peaceful, restorative depths of slumber, the quiet hum of an endlessly expanding universe, a testament to cosmic resilience and its grand, unhurried rhythms, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most distant reaches of cosmic time, forever guiding us towards a serene and tranquil cosmic destiny. Now, let's explore even further the subtle, graceful dance of these cosmic events in the universe's distant future, as entropy gently guides everything towards its ultimate, serene blending. Imagine the very last star in the universe, a tiny, cool red dwarf, having burned its fuel for trillions of years longer than our own sun, finally winking out, its last gentle photons dispersing into the vast, cold darkness. This silent event, though seemingly small, marks a profound transition. As the last active source of light yields to the pervasive stillness, after the stars have all faded, the universe will be dominated by the cold, dark remnants, white dwarfs, neutron stars, and black holes. Over unimaginable stretches of time, even these remnants will undergo further, subtle transformations. White dwarfs will slowly cool and solidify into black dwarfs, perfectly cold, dark, and dense spheres, no longer emitting any light or heat. Neutron stars will quietly persist, incredibly compact and dense, but their active lives long since concluded. Black holes, as we explored, will continue their imperceptible evaporation through Hawking radiation. A process so slow that even the largest supermassive black holes will take quadrillions upon quadrillions of years to finally dissipate, releasing their stored energy back into the void as the gentlest of whispers. As these final celestial objects dissolve or fade, the universe will become an increasingly dilute sea of fundamental particles, photons, neutrinos, and other subatomic remnants, endlessly drifting further and further apart. The vast space between them will continue to expand at an accelerating rate, driven by dark energy, ensuring that these particles become more and more dispersed, their interactions becoming incredibly rare. The concept of distance will stretch to unimaginable scales, and the very idea of neighborhood will dissolve into a profound cosmic solitude. This is not a dramatic end, but a final, gentle unraveling. There will be no more heat to flow, no more processes to occur, no more stars to form, no more light to gather. The universe will reach a state of thermodynamic equilibrium, where all energy is perfectly and uniformly spread out, perfectly balanced, perfectly blended. It's like a vast, ancient symphony that has played its final, longest note. And now the echoes have gently faded, leaving behind only profound, eternal silence. This ultimate state of maximum entropy is the culmination of time's arrow, a universal stillness where all distinctions have gracefully dissolved. Consider the profound patience of these cosmic processes. The dissolution is not sudden or chaotic. It is an infinitely patient, gentle unwinding, unfolding over timescales that make the current age of the universe seem like a mere fleeting moment. This unhurried nature allows for the subtle interplay of forces to play out with exquisite precision, guiding the cosmos towards its ultimate destiny with a serene, inevitable grace. The universe, in its boundless wisdom, is not rushing. It is simply flowing along its most probable path, guided by the unseen hand of dark energy, a cosmic journey of ultimate peace, a general historical fact that highlights the ongoing refinement of these future scenarios. While the broad outlines of the Big Freeze are widely accepted, theoretical physicists continue to explore various subtle nuances and potential exotic phenomena that could occur in the extremely far future, such as the possibility of proton decay or the behavior of matter at temperatures incredibly close to absolute zero. These delicate explorations push the boundaries of our understanding of fundamental particle physics and the very nature of matter itself. Here's a lesser-known detail about the potential role of quantum mechanics in this distant future. Even in a state of maximum entropy and near absolute zero temperature, quantum fluctuations would still exist. Tiny, ephemeral virtual particles would continue to pop into and out of existence, even in a perfectly cold, uniform cosmos. This suggests that even in the ultimate stillness, a subtle, almost imperceptible whisper of activity might continue, a final, gentle hum at the very edge of nothingness, reminding us of the persistent dance of the quantum realm. It's like a perfectly quiet room that still holds the faintest, almost imperceptible echoes of its past, eternally murmuring. And for an ongoing academic debate, cosmologists are actively debating whether the universe will truly continue to accelerate indefinitely, leading to the Big Freeze, or if the properties of dark energy might subtly change in the unimaginably distant future, leading to other scenarios like the Big Rip, or even a Big Crunch after a period of contraction. Understanding the precise nature and ultimate behavior of dark energy is the key to fine-tuning our predictions for the universe's most profound and beautiful final secret. This intricate and beautiful puzzle, gently inviting us to understand the subtle wisdom of reality's grandest rhythms and its profound challenges, continues to guide cosmic inquiry. So, as you continue to drift, allow your mind to gently contemplate the universe's quiet, expansive future, feeling the profound peace that comes from understanding how its boundless journey gracefully leads to an ultimate state of cold, dark, and tranquil solitude. Let this understanding cradle your consciousness, like the serene, unwavering rhythm of cosmic expansion itself, gently stretching and accelerating as you gently surrender to the peaceful, restorative depths of slumber. The quiet hum of an endlessly expanding universe, a testament to cosmic resilience and its grand, unhurried rhythms, is now your lullaby. A soft reassurance that wonder and mystery exist even in the most distant reaches of cosmic time, forever guiding us towards a serene and tranquil cosmic destiny, inviting your mind to gently dissolve into the vast, peaceful embrace of the cosmos.